At this point, we get to start our first experimental session. And many sessions can be done in different orders, but this is usually the one you'll do first. Now, the reason is that we want to start to figure out getting all your tools and setup all in good shape. It's also the time when you need to take a look at your experimental setups and experimental tools. So, for example, if you're using this development board, which would have been available heavily in, say, 2019 timeframe, most of your IOs are on this side and a few jumper pins over here. So this would be a larger picture of that board where you can see the FPAA, the connectors, where the USB connection is, and if you're curious what the FTDI chip is. You can see where everything is all in place here. There's a few IO pins over here that are duplicated here, so you might find that useful. In general, I would say for using the board, I would not use this. Most boards are typically, at this point, designed to not have these kinds of issues. Depending on which board you're using, though, you might have to watch and look around at your various aspects. We're talking about pin 1, 2, 3, 4, and 5 are the ones you typically are going to use for a lot of the code, and we'll proceed from there. You might also have a scope-like device, like an analog discovery block. So you're talking about like an analog discovery element. And again, you want to watch where are my input scope channels, like for 1 and 2, plus and minus. You might be curious about where are my voltage supply, where are my signals, like W1 and W2 for the waveforms, and a few other things that you may end up wanting to use on this. There's a whole bunch of digital I/O, but start to know where your tools are. Fortunately, for a lot of the things that you're doing, you could get away with probably 1 or 2 USB controlled structures running off your laptop, and all of this works great. So then the question becomes, all right, so what kind of things do we want to do? Well, one of the first things you want to be able to do is bring up your FPAA tools. So make sure that you've downloaded the tools. Make sure that you put any additional sort of communication or hardware patches in it that are required. Make sure that you can actually bring up the tools and that they actually are operating. Okay. So in particular, if you are using the Scilab XCOS tools, make sure that you can sort of get the infrastructure up. If you're using it in a virtual machine, bring the virtual machine up and continue along in those paths. Everything should be fairly straightforward, but again, make sure you have those elements, and if you need to, look at some of the other documentation and or videos that are in this space. So then what we're going to do is we want to see if everything works correctly. So you'd want to start with the very first thing, which is a DAC ADC, and see if we can actually get that compilation to work. Compile it, then we actually program it. One of the big things with the programming is it really gives us a real good test on how well your USB connections are working. One of the most challenging aspects of this entire hardware infrastructure is the USB communication. We've spent a lot of time working through this, but that is one of the big areas you need to think about. For example, if you have a fairly modern machine and it's running with USB 3, make sure that if you're running a virtual machine that you use the USB 3 drivers. Otherwise, you're going to start having some issues. And different USB topology structures are going to get better, most likely. So hopefully this becomes less and less of an issue over time. But this is one of the things that you want to be paying attention to. So we want to be able to program it, which then tells us how well our communication is going, make sure all the programming is behaving as you would expect. It probably takes, at least at circa sort of this level board in 2019, it'll probably take about a minute to program. It's not very long, but just be patient with it. And then you want to measure and look at the DAC and ADC block, and you would expect that I would get a ramp of inputs and I should get a ramp of outputs that look a lot like the input. Hopefully that's what you see. And so that is a really good sort of self-check to make sure that you're getting what you think you're getting. And then what you also would want to do, particularly if you have a scope block to work with, is compile up one of a couple different structures where you can, or draw it yourself, where you can actually go from an I/O pin to an I/O pin externally and actually measure what does that look like. And the other thing that we want to look at is look at the behavior of a low-pass filter block. And we may want to look at that through pins, but we also would want to potentially use the example file that's there that has it going from basically an on-chip basically an on-chip arbitrary waveform generator, and goes to an on-chip measurement DAC. And then you can actually see what is that low frequency transfer curve. You can actually look at what the step response is. Usually the input for it is you're set up to do the step response, so you can just do that right away. And you can take a look at it. Now, always be careful that the bias current or frequency it's being set to might be a little low, because we try to keep it in nice and slow so you can see it. You might need to speed that up. So don't be afraid to play with stuff, because if you kind of know where the initial parameters are, you can always regenerate it. That should not be a problem. If you need to, you can of course always reload the entire system, worst case. So it takes a little bit of time, but in the end, there's not a lot of fear in terms of what you're doing with the code of what you can actually normally touch. There's some things that, for advanced users, you can get some more interesting effects, but for the most part, you're going to be okay. So don't be afraid. Try to work with things and try to have some fun with the structure.